Okay, guys, in this video, it's going to be a quick one. We're going to review the five general types of chemical reactions that you can have in a basic chemistry class. So the skills that we're going to need to move forward to understand these things are the stuff from last unit. We're going to need to be able to write chemical formulas for ionic and molecular compounds. An example of what I mean by that is we have to realize to go forward that, let's take lithium for example. Lithium, remember, exists as a +1 cation, and oxygen exists naturally as a -2 anion. So if we need to write the formula for lithium oxide, it's not just simply LiO, it's Li2O. That would be a neutral compound of lithium oxide. The other skill we're going to need to do and incorporate is stuff that we've done more recently. That's to develop and balance the skeleton equations. Okay, so let's go ahead and get going. The first type of reaction that we're going to talk about is called a combination or synthesis reaction. Some textbooks, sometimes you'll also hear it as a composition reaction, but the name sort of says it all. If we can understand what combination or synthesis means, we understand what this is going to look like. We're combining something, or we're taking two separate elements and synthesizing them into one. So the characteristic is simply that. Two or more substances react to form a new single substance. So in this slideshow, we're always going to show us sort of the generic formula of what these types of reactions would look like. This one you might be able to guess would look something like this. Substance A, or element A, plus element B would react to yield a new compound, A plus B. So two things are forming something larger. A plus B yields AB. So let's do an example then of what we see there. Well, one of the things that we did at the very beginning, it's always a crowd pleaser with a high school chemistry lab, is burning magnesium. You get that super, super bright flare up that you got to look away from. This is actually a combination or synthesis reaction. So let's see what that would look like. Magnesium might represent element A, and we're going to combine it with oxygen under a lot of heat. So remember, sometimes we put that descriptor over the yield arrow. Here's something that we would need to know beforehand, though. Oxygen in the atmosphere doesn't exist as just plain O. It exists as plain O2, right? Diatomic oxygen. So they're going to combine together after this reaction to form magnesium oxide in that case. And that is the correct formula for magnesium oxide, MgO, right? Magnesium is a +2 ion, oxygen's a negative, so they would form that way. But the equation's not quite balanced. Pretty simple to do it. This would balance our equation. And again, that's a skill we should have prior to this video. So when we do this, typically we would light the magnesium metal on fire in the presence of oxygen, and we would usually put that thing, right, if you remember, we put all of that into a crucible and we're left with ash. Well, that ash was mostly magnesium oxide, so that was the product in this case, and that's a combination or synthesis reaction. Let's do another one just for the sake of being thorough, maybe. We might have a combination or synthesis when we talk about producing water, right? It's a real important one. Water is hydrogen plus oxygen, and it's going to yield good old H2O. But again, we got to think a little bit more about this. In nature, hydrogen and oxygen always exist as a diatomic molecule or diatomic gas. So in this case, we need to balance this equation. And again, balancing this equation is pretty simple. The balanced equation would look like that. Right? So those are definitions, or examples rather, of combination or synthesis reactions. So you might want to think of the next type of reaction, a decomposition reaction, as the reverse of a synthesis or a combination reaction. In this case, we're going to take a single compound, so that's two or more elements put together, and we're going to break them up into simpler substances. This does usually require energy. One thing that we did at the very beginning of the class, we saw the electrolysis of water, where we took water, a compound, and broke it up into its constituent elements, hydrogen and oxygen. The generic form of this equation would look like, maybe you have guessed it, it would look like the compound A and B, and it would decompose to A plus B. A couple examples. Let's just do the water one, right? H2O can be broken into hydrogen gas and oxygen gas. And again, to balance this, we would expect 2 waters for every 2 H2s and 1 O2. And again, to be thorough, we'll do another one. Let's think about something more obscure, maybe mercury oxide. Mercury oxide would look something like this, HgO, and we would heat it up. Doesn't have to boil or ignite, but just heating it up would allow us to split it up or decompose it into hydrogen and oxygen. And again, oxygen always exists as O2 and O2 gas. We might start putting those there. Mercury is the special one. It's a liquid at room temperature. So again, we need to balance this equation, and that's pretty easy to do. A balanced equation might look something like that. And again, real simple idea, decomposition, taking something large, a compound, breaking it up into its component parts. Okay, the next one, a little bit harder to recognize just by looking at the equation, is called a single replacement reaction. And the characteristics are both reactants and products will consist of elements and compounds. And we can have these reactions with metals or halogens, and we'll see an example of what that looks like here. A metal can replace another metal in a compound, or a halogen can replace another halogen in a compound. The generic form of this equation, a single replacement reaction, would look something like this maybe. A plus BC, those are the reactants, and this reaction could yield A replacing B and combining with C to liberate B. So that might be the generic form of a single replacement reaction. So one reaction that we did in our lab and we witnessed this was the reaction between iron and copper sulfate. So that would look, I'm going to write the skeleton out here, that would look like this. Here's iron plus copper sulfate, CuSO4, and let's pause this to see what we have here. A might represent iron, B would be copper, and C would be sulfate. And then we're just going to follow the other side and recombine them here. So I'll do it a little bit subscripted here. We expect then A to bond with C, so that means iron will bond with sulfate, and we will be left with just regular copper. And if you remember that reaction, we saw the copper plating on the iron in that solution. So that's a single replacement reaction. And again, here's A, here's C, and here's B. A, C, and B never change their meaning. They just recombine. So that's a single replacement reaction. So what we have these tables here for when we looked at in our book is that there are some rules. Not just any metal or any halogen can replace another one. Only a metal that is more reactive or a halogen that is more reactive can replace a metal or a halogen that is less reactive. That means when we read these tables here, if we take a look at this one, we would expect potassium to be able to replace iron, but we wouldn't expect iron to replace potassium. So let's take a look at what we just said. We looked at iron here, and it replaced copper. Copper is less reactive, so that we do expect, and we did see that happen in the experiment. Same is true of the halogens. If we go down here, fluorine we would expect to replace any of those halogens. Chlorine could replace bromine and iodine, but bromine could not replace chlorine or fluorine because of their reactivity. So let's do one more single replacement reaction just for thoroughness. Also in our lab, if you remember, we took magnesium and we put it in hydrochloric acid. So that might look like this. Element A could be represented by magnesium, and hydrochloric acid is HCl. If you remember what happened, we got a salt, we got magnesium chloride, and then we used the splint test to test for a gas, and lo and behold, we found out that it was hydrogen gas. In this case, it's not quite balanced, but it's really easy to balance it. That would be the complete balanced chemical equation, almost like that. Wait a minute, guys, that's not right. I didn't use the right skills coming into this, right, that I told you that we needed to do. Let's scratch this. We are close. Mg plus HCl Magnesium chloride will actually exist like this. This we can balance correctly. So this is actually even simpler to balance. That would be a balanced equation. 2 hydrogens, 2 chlorines, 1 magnesium on each side. Okay, so let's look at this one in context of the chart that we saw last time. This one would happen. We would expect this reaction to happen. We see that magnesium replaces hydrogen to bond with the chlorine to produce magnesium chloride. That's expected, right? Here's magnesium, here's hydrogen. So magnesium is more reactive than hydrogen, so it should replace it. Here's kind of maybe a trick question you might see on a chemistry quiz or an exam. What if we had this? What if we had zinc plus MgCl2, so magnesium chloride again. And then you could start going and plugging in on this, but then if we look at our chart, we're looking at zinc here. Here's zinc, and magnesium is up here. Zinc will not replace magnesium. It's less reactive. So the answer to this is no, we shouldn't have any products. It won't actually happen in nature. So we might just say, hey, this reaction does not occur. So the last reaction we're going to talk about today, we'll leave combustion for later, is a double replacement reaction. And this is the exchange of positive ions or metals between two compounds. The metals actually just switch spots. Typically this will give off a gas, or it might produce a precipitate or form a compound like water. But the generic equation then for a double replacement reaction might look like this. A, B is the compound, plus CD is another compound. And A and C are just going to switch spots. So we get AD plus CB. You can see what's happened here, right? A and C just switch spots. They're combined with the other non-metal here in this case. So this is called a double replacement reaction. And again, a lot of times it will yield a precipitate or give off gas or another compound like water. We saw, as an example, when we talked about this in class, this reaction, that is lead iodide. And let's take a look then as that as an example. We got that pretty yellow precipitate by combining lead nitrate to begin with. Lead nitrate, remember lead is Pb, and nitrate would be NO3, and it would be 2, that's lead nitrate, and it was in an aqueous, a clear solution. We couldn't see it, it just looked like water to the naked eye, and we combined that with potassium iodide, Ki, and that also was in the aqueous solution, clear liquid, couldn't see anything. But when we mixed them, we got that beautiful yellow precipitate, and let's figure out which one of those it would be. So lead is going to be recombined, right? Lead is A, and it's going to be recombining with D, and D is iodide. So we'd expect to get PBI, and it would be PBI2, plus potassium is going to recombine, so C will recombine with B, and that's nitrate, NO3. And that would be the formula for that. That's a skeleton equation. It's not balanced yet, but this is the balanced equation then for that. This should balance it. So these two are aqueous, these two are aqueous. Here's the thing, we haven't gone over solubility rules yet, but this is solid, and this is aqueous. This was the precipitate. So a lot of times having those descriptors, aqueous, S for solid, L for liquid, G for gas, is really helpful in thoroughly explaining the reaction, because if we see S coming from two aqueuses, we know that that's a precipitate, and that's pretty common in a double replacement reaction. So we'll do one more just to be thorough here. Again, this is one that we did in our lab. We combined barium chloride with, which is this, with sodium sulfate, and it yielded barium sulfate and sodium chloride. So again, just to get a feel for what went on, we have barium represented by A, chloride, B, sodium, C, and sulfate is D. And what do? They just recombine. Here we get A and D, and here we get C and B. One of the things you remember from this reaction maybe is you got this milky substance, these two clear liquids, and then all of a sudden we got this milky substance. That's the solid. That was the precipitate. So that's very common in a double replacement reaction. We will do combustion reactions later on Friday or next